All right, guys. Are there any questions over any of the assignments so far? Well, assignment so far. What we're looking at today is still continuing on with exponential growth and exponential decay. Now, what goes along with that is the natural base e. This is dealing more with logarithms, or real natural logarithms with its base e. Now, e is something that we've talked about before, because when we talked about irrational numbers, I mentioned pi e square root of 2. E is considered one of the irrational numbers. It's kind of grouped together in kind of a special group. But e is an irrational number and can be represented or closely represented by the formula 1 plus 1 over x to the x. This is kind of the formula for finding e. Well, not actually finding, but approximating. Because the value of e, this here will approach its actual value. Now, the value of e is approximately 2.71828182846, approximately. Because, again, it is an irrational number, so there's no way for us to actually get the exact value. We can't represent it as a fraction. But e is irrational, and this is kind of the value. Now, e, we can kind of treat it like a variable, just like we can with pi, because we can say pi squared, pi times pi, or we can do things with pi. We can do the exact same thing with e. So if I wanted to simplify e to the third times e to the sixth, you get e to the ninth. Because whenever we multiply like bases, we add the exponents. So 3 plus 6 is 9. 16e to the fifth divided by 4e to the fourth. Yes, because 16 divided by 4 is 4. Whenever we have like bases, we subtract the exponents, so 5 minus 4 is 1, or we can just say 4e. Now, whenever we type it into a calculator, if we were going to type it into the calculator, we have to type 4e to the first. It wants an exponent with it. In most cases, it's expecting, the calculator is expecting there to be an exponent. So if the exponent's 1, we have to type 1 in. And the last one, powers of powers. Well, here we would have, apparently I'm going to scroll. Well, we would have r3 squared. Now for e, we're going to take the negative 4x and multiply it by 2, because powers of powers multiply. Now it's going to scroll down. Now 3 squared is 9. Negative 4x times 2 is negative x. But we can't leave exponents negative, so to make it positive, we move it from the numerator to the denominator. And we get this here. Any questions on these here? So if we look at this next one here, e to the 7th times e to the 4th would be e to the 11, because 7 plus 4 is 11. Well, hopefully 28 will divide by 8 evenly. Because we can subtract exponents. 8 minus 5 is 3. So we get 3e to the third. And the last one here. So we're going to do the same thing we did before. So we'll apply the third power to both. So we'll have 10 to the third times e to the negative 3x times 3. Well, 10 to the third is 1,000. And then we would have e to the 9x. But we can't leave it as negative 9x. To make the exponent positive, we move it from the numerator to the, it gives us e to the 9x in the denominator. Any questions on this here? Let's look at one last one. Let's say the 4th root of 10,000 e to the 16x. Can we take the fourth root of 10,000? I know it's not on the paper, but I'm adding it. Well, we can plug that in the calculator, yes? What times itself 4 times is 10,000? 10. 10 to the fourth is 10,000. Now we need to take the fourth root of 16, or e to the 16x. Now we can kind of refer back to our nth root of a to the x, which is a to the x over n. In our case here, that would be e to the, what's going to be on top? 16x, and it's going to be over. Still have 10, we'll still have e. 16x over 4, will that reduce? 16 divided by 4 is? 4x. That's it. Questions on this here? Any questions over anything we've done so far? Now we can still consider these functions as either exponential growth or exponential decay. Now they come in the form y equals a e to the rx. It's called a natural base exponential function. Now e, as we already said, is 2 point something. It's greater than 1, yes? So by definition, y equals e to the x would be considered what? Exponential growth. Well, there's no real way for us to change the value of e because e is set, it's a constant term. But if we make the exponents negative, then it's actually going to be exponential decay. And it works pretty simply. Because y equals e to some x, we can say 4x. This here would be growth, because it's just e to the 4x. Now if we said y equals e to the negative 4x, well, again, we can't really leave exponents negative. We need to make them positive. So what I can say is, well, this is 1 over e to the 4th, and this whole thing is to the x. Well, 1 over e to the 4th, is that now less than 1? Well, yeah, so the denominator is bigger, so this is going to be decay. So it's almost a little bit easier than exponential growth and decay when we didn't have a base of e. Because when we look at these here, so the first one here, y equals 3 to the x, 3e to the x, would this be growth or decay? Because the x is positive. Because the base is greater than 1, e is greater than 1, but the exponent's positive. Because when we look at a base of e, we're looking at the exponent being positive or. So the next one, e to the negative 0.5x, would be decay. And it's based not so much on the value, but the sign. So these are our first two here, 3e to the x and e to the negative 0.5x. And if we graph it, the blue one, our 3e to the x, looks like our exponential growth. As we go from left to right, it's slowly getting bigger and then increases faster. And the one in red is our exponential decay, e to the negative 0.5x. And we see it does decrease. Now, it's not based off the fact that we have 0.5. It's more based off the fact that it's negative. So I can delete that 0.5 and just say negative 5x. Hit graph again. It will change the function, but it's just now steeper instead of kind of a more gradual slope. Still the same thing. It's more based off the sign, not so much based off the specific value that it has. So if we looked at number 4, this would be growth. Number 5 is questions on these here? No. Because really, to graph it, it's just, okay. I'll erase this here. If I wanted to graph this, well, when x is 0, this here is going to be at 1/2. Because anything to the 0 power is 1. 1 times 1/2 is 1/2. And then finding the next point is not going to be nice, because if I wanted to somewhat cheat and say this is 1/2 e, then we can get this here. And the reason I say that is because 1/2 second ln is where we get e to the first. We get 1.3591409. It's not a nice number. Again, e is irrational. We can't get nice numbers. And most of the time, there's a graph, so it's just copying that down. I don't see a whole lot of use in doing that. Any questions on these here? So, let me see. Right, those are different. This is the natural base E, and the one that you're talking about is an exponent or a variable E. Because if we do, not a sign, alpha E, enter 0. Now if we go second E to the first, we get this here. They're actually, the capital E is a variable we can assign a value. I mean, if we wanted to, we could make it so that it does work. So I could say second E to the first store. Oh, if I can type that in right. Second E to the first over 1 store. Now they're the same value, but they're different. Does that make sense? Essentially, any of the other letters are going to be the same as that capital E. This E is special. Any other questions on this here? Now, we're not going to dig too deeply into this, but we can actually calculate compound interest or continuously compounding interest. So this is if we were talking about trying to see how much interest has occurred over 365 days. So the formula that we had yesterday, P times 1 plus R over N to the NT, it's using this formula, but N in this case is 365 days a year, every day. So this is a little bit easier way to calculate it. But we're not going to delve too far into this or really look too deep into this here. But this is one calculation that we can do for interest. Most likely, especially in the PFL class, this might come back up. I remember this, the way that I keep this formula straight in my head is PERT. P-E to the RT, P-E-R-T, PERT. Is one way to think of it, but we're not going to focus on that there. That's all we're doing for today. The rest of the chapter sections aren't going to be this short and condensed. Really, we could have done yesterday and today in the same day, but oh well. So on page 311, problems 4 through 10, even, and 15 through 20.